Go ahead.
Hi, everybody.
This is Yao Zhen Lin, representing the SEDIMENT project to talk about how the sediments could help in the 5G, in particular, to make sure that the IoT devices with restricted resources can be attested and trusted in playing a role in the 5G applications. Okay, so just give you guys an overview of what the SEDIMENT is about. It's as I said, it's primarily targeted and the resource constrained devices, because those are presenting a weak link in the security chains. We can see that IoT devices is here. And we have a 5G course here, applications somewhere sitting there, and there's the various things in between them. And the concern is that if the IoT devices compromise, they could create these threats into either the piracies or the securities or the 5G core. And so that's where we place our emphasis on. In the SEDIMENT projects, by the way, it is DARPA's supported program, a part of DARPA supported program for the Ops 5G program. So what the SEDIMENT provide, one component of that is the scalable cryptography. That's for sending the secure publications from the IoT devices all the way down, up to the application server. The other portions of it is the remote attestation, which with some components, entities within the infrastructure be able to make sure that the IoT devices integrity can be trusted. So this is done through remote attestation. And of course, in order to do that, we need to have a root of trust on the devices itself, because it's resource limited, and so a lot of common security practice would not be able to apply there. And so we need to rely on certain supports of the root of trust in the device to give us that kind of guarantee. And so those are the three main components in the SEDIMENT program. And currently we are in the second phase of it. There's a third phase, which is more into the actual applications to and integrations into the 5G infrastructure. And as part of this activities, we have several transition activities going on. For the very first thing is that we, in the beginning of this year, we just created an open source project under Linux Foundation. And the reason I've been presenting our ideas here is definitely try to exploring the alignment with the 5G super blueprint. And we also want to note that the solutions that we come up with is a strong alignment with the IETF REDS architecture. REDS is a remote attestation architecture. And certainly we have been doing various demonstrations in our own testbed, and also we also exploring possibilities in demonstrating it within the Linux Foundation testbed, in particular for the activities within the in the phase 3. Overall, basically, SEDIMENT is trying to provide a combination of software root of trust, remote attestations, and the cryptography to be able to apply to the zero trust security system. In particular, we wanted to be able to scale across heterogeneous computing platforms, in particular for the resource constrained IoT devices. Okay, so for this presentation, so let's focus on specifically for the remote attestation portions of it. As we said, the goal of it is try to detect the presence of any malware or the software tampering on the IoT devices. And the IoT devices, we have the remote attestation protocols for communication between all other logical entities sitting in the infrastructure. We sort of lump together here, called the rep server plus the verifier. In fact, there are several logical entities in there, and you will see in the next slides. And the purpose of that is that assuming the IoT devices can be logically create this through the remote attestation, through the root of trust, we will have a privileged area where the attestation code reside plus keys, and that any unauthorized access will trigger activities and to notify the entities within the infrastructure. And our goal is to make sure that in the application area, where any kinds of malwares or obsolete codes or miscommunications will be detected and tested and detected by the attestation code. Okay, and for the key components of the RA, there's a protocol we are going to show you on the next slide that essentially will have two authentication components, but most importantly, will be able to request any kinds of device evidence from the IoT devices and be able to say, okay, yeah, I think that's what we expected, and or yes, those are being authorized. So that includes things like firmware fingerprints or software configurations or even the process status. And so those are the information that can be requested from the verifier in here to the IoT devices, and through the attestation code, they will be able to provide those evidences back to the verifier. And of course, as I mentioned, that for this to be trusted, we need to have root of trust support, and some lower level devices that doesn't have any hardware, software, and so we need to build on top of those. And so there's a different combinations of the things that we can do, but ultimately, what we'll like to have is that the root of trust solution for a particular kind of platform can give us this set of guarantee, meaning that when we're running the attestation codes in there, the attestation credential, such as the things that are sitting in here, it's only authorized to be accessed by the attestation code itself. No other component can try to steal the key from there. And there's no leak or anything in there. And also we want to be sure that the code itself is run in automatically, because if you allow any other process to sort of intertwine with it, then there's always a potential that certain information will be changed and before the attestation is completed. So those are also the key components as part of the guarantee for the trust. And those are the properties that we have to make sure that we have a solution for it for different kinds of devices. Any questions so far? Okay, so at high level, the protocol itself is kind of simple. I mean, here is like, okay, the prover will give will initiate a request, and once it's authenticated, the verifier will send a challenge within this challenge itself, different kind of evidences will be requested. You can randomize or do anything to sort of make it dynamic instead of a fixed pattern instead of going to the prover. And based on information, certainly prover needs to make sure that it's coming from the right verifier. And once they be able to do that, then you will provide the evidences based on the challenges, and then verify using its store information to be able to say, yes, I think the prover has all the right things, or no, I don't think the prover has the right thing. And so if it is yes, then there will be a passport granted to the prover, and the prover at that point will be able to use that passport to send it to the relying party, get a permission to send the data through, and after that, then you can proceed to send the data through the relying party. The relying party, in a way, you can consider that as a logical entity. It could be a firewall, or could be a network access point, or could be anything that need to know that whether IoT devices can be trusted or not before let the traffic through. Okay, and this portions of it is adding more flexibilities in terms of how to pair the approvers and the verifier, especially in the very sort of large deployments where you have many instances of verifier that can do things, and there are huge numbers of approvers. And there are situations where you don't want the information to be stored physically or statically inside the prover, such as keys. So there's additional mechanism that decides who the prover has to talk to the verifiers, and what credential they need to use, and that kind of things. And or even for the verifier to be able to know that what are the current expected evidences results. And those will be done through the managers. And we just put a logical entity here, but essentially it has all kinds of activities that's related to a success remote testation when we deploy it. Okay, so as I mentioned, we try to align with the IETF REST architectures. So this is the general form architecture for the REST. And so you have a testers, we would name it as a prover, and provide the evidence for verifiers, and the verifier has a testation results and then shared it with the relying party. And the things on top are, for example, some endorser that can endorse what the verifier authenticity of the verifiers. And there are entities that will provide the reference values so that verifiers knows what's expected from a particular IoT devices. And the verifier's owner can set the policies in deciding what to do with it. And then even the relying party owner that will have their own policies and deciding what happens if the if a particular IoT device is what's going through this process and have certain kinds of testing results. So what should we do with it? Right. And so this is the IETF REST architectures. And as we mentioned that we follow the passport model in the sense that the prover, once they provide evidence, and if it's good, then the result itself, including a passport, and the attester will be able to submit that passport to the relying party, and then relying party can validate that particular passport, including whether it's coming from a trusted verifier, etc., and before applying the policy. Okay, and as far as the type of the evidences that we have been supporting, certainly it includes either full or partial firmware HMAC, and the firmware versions or the BIOS versions, etc. When it's booted, what's the geolocations of the device, and what's the current software configurations, or even things like any kinds of user-defined functions that we can do in order to do the runtime integrity checks, like what are the processes that's going to run in there, what kind of resources usage status, etc. And as I mentioned, those are the list of the evidences that we support, but the verifier can decide and pick and choose a particular type of evidences they can even at given point in time. One is to randomize it, and secondly is to minimize the efforts that the IoT devices need to come up with. And we are also in the process of creating the API features so that not only our code will have to be theirs, we also, for example, things like a reliant party, if we link it with other management system for dealing with a firewall or dealing with the network access, they might want to access, have the ability to access what's the results, and also in terms of things like device reference values that the verifier needs to have, or any kinds of appraisal policies, those will also need to be integrated. And so we are in the process of providing those APIs for the third-party applications when they need to use this remote attestation features. Is that okay? Okay, so in terms of the transitions, we, as I mentioned, we currently have open source projects created under the Linux Foundation, and the current focus is on it's remote attestations, but gradually we are going to extend it, also including the scalable encryptions in there, and so here are the documents that have been adopted and also clears, and then here is the link to the repository for our codes and web pages. And as I said, I mean, this is just recently announced in February. And for our engagement with the 5G Super Blueprint, we work with the Madasas and Irani to come up with the use cases. And in particular, one is to ensure that IoT devices on the network are authentic, meaning that they have the right firmware images, etc. And the other is that to more dealing with the deployment to see whether the IoT devices has been sort of when the new things added or updated, how would the information actually been propagated, and so the 5G core knows where it is and what has happened, and to be able to conduct it, report attestations afterwards. And this is what we have identified, and then we are in the process of integrating the remote attestations onto the existing Super Blueprint lab infrastructure. It's a way of realizing those use cases. And particularly for the use case one, this is the sort of main focus of the discussion today. The IoT devices on the network, we want to make sure that it's authentic and also it has not been tampered with. And how will remote attestation help in this case? So imagine that you have a camera on the remote area that's providing informations. And then we want to have the I verifier, which is in the infrastructure entity, part of the infrastructure entities, and it says to periodically inspect this camera by doing the attestations. And then if the result is successful, then the camera can, the traffic data from the camera A can be sent through the application sitting in the 5G application server to be able to sort of take that and process it. But if the attestation failed, this case, then I'm sorry, then IA is going to alert the relying party. For example, in this case, we can consider it as a firewall or any kind of network access point, or even in a more the more realistic cases, we may be able to sort of integrate it with AMF to be able to say, okay, yeah, the traffic coming to here, but the AMF is going to initiate the process to block that particular traffic. And what are we doing with CubeArmor? So in this particular case, remember we have the verifiers and we have the relying party, we have application servers, we have the prover, and as I mentioned, the use cases is like for the camera, when it's been tested successfully, it can send the traffic through the relying party all the way to the application server. And the verifier is playing the role to decide that whether this camera itself can be trusted or not. And as a first step, we actually create a surrogate prover so that the communication here is between the verifiers and the provers, and the prover is sort of representing what the real camera device as a first step. And we have also identified all the different ports, and the CubeArmor come in as a way of making sure that all the behaviors within the verifiers and the relying parties, application servers, or even traffic from the prover coming into the verifiers what has been expected. And there's no additional access or additional or suspicious behaviors that sort of tampering with all those components that are sitting in the infrastructure. Okay. Any questions, comment for this particular use case?
I think it's very good. Appreciate you including the CubeArmor. I think it's very important that if entire system relies on app server, verifier, and relying party, that those component itself should be protected. And I think you're bringing into two capabilities that will help him immensely.
Yes, thank you. So at this point, I'm going to give the floor to Raul, who is going to talk about what they Acronauts have been able to do with the containers that we provided to them in terms of the containers for the verifiers and relying parties and app server. And we also create a container for the prover, and they will be able to see what the behaviors of all the communication between them.
Thank you, Jian. Can I share my screen?
Yeah, go ahead.
Thank you. Okay, so hello everyone, I'm Rahul Jadhav. So let me take a step back, and Jian has already started made sure that the context of KubeArmor is placed properly. I want to take a step back and explain what KubeArmor is, what is the problem statement that we started off with, and what our eventual goal is. So KubeArmor is a CNCF project today. It was donated to CNCF like a year and a half before by Aquinox, still led by Aquinox, but there are other maintainers for KubeArmor as well today. The primary problem statement is about container isolation and hardening, or pod isolation and hardening in the context of Kubernetes workloads. The problem that we see with 5G control plane or edge workloads in general is that we will have multiple vendors pushing in their workloads towards edge, or in the context of 5G control plane. And as a service provider, the service provider has to make sure that even if a particular workload has any security gap, it should not impact the whole control plane, or it should not impact the other workloads on the same edge deployment. So how do you ensure container isolation? How do you ensure that the blast certificate is limited? So that's where KubeArmor comes into play. When we started working on KubeArmor, our primary intention was not only just observability. Of course, observability is the key element and comes first before we start enforcing the policies, but we also wanted to have a system in place which could do inline mitigation. And I'll talk more about it in the subsequent slides, but not only observe, but prevent attacks and how prevention of that attacks looks like. I'll explain the subsequent slides. So that there are two types of policies that KubeArmor can consume and protect, can be used to protect the workloads from. One is the hardening policies. These are the policies which have explicit block or audit actions. Now, you have existing security controls from MITRE, from ENISA, from PCI, CIS compliance frameworks and attack frameworks. How do you convert those mitigation rules into KubeArmor policies and apply it on the workloads? That's point number one. And then the second point is, how do you understand what the workloads are doing? And based on that behavior, create a zero-trust security posture wherein you only allow that workloads to do the stuff that is identified as part of that behavior. So that these are the two intentions. And of course, with the least permissive policy settings, the end goal is to have an ability to even protect from zero-day attacks. So tomorrow, if you have a command injection attack, and if an unknown process is tried to be executed, it won't be allowed to be executed in the first place. So with that in mind, let me just go on to the next slide. This is the overall architecture of KubeArmor. Like there are two primary components, and this is in the context of the architecture diagram mentions Kubernetes, but it works equally well for non-orchestrated containerized workloads, which is what essentially we are working with the SEDIMENT team, where we have a virtual machine, and on that virtual machine we have a set of container images that are deployed. But we started off with Kubernetes native design in mind, and if you ask me today, it's more friendlier. The policy enforcement and the Kubernetes resource model is something which is effectively been made use of by KubeArmor to do two things. One is to get the security intent, and then to apply the security controls. There are two aspects in the overall architecture. One is eBPF, which is used to understand what the workloads are doing without actually changing anything inside the workload itself. And then using the information from eBPF and knitting it together with Kubernetes metadata or container metadata, such as labels, namespaces, and things like that. But this part is pretty standard. There are other engines also which can do that. But what is differentiated in the context of KubeArmor is the inline mitigation, where it is possible for you to specify a set of rules saying only these set of actions are allowed and everything else is either denied or audited. And KubeArmor under the hood uses something called as Linux security modules. Traditionally, Linux security modules has been extremely difficult to deploy. The AppArmor and SLNX have been notoriously famous for making it complex, such that administrators have been turning off the solutions, turning off these primitives rather than enabling it. The aim of KubeArmor is to abstract away these LSMs under the hood and provide a Kubernetes native model, security model from policy perspective. So that's that's that. So what is it that we intended to do with SEDIMENT? First is, of course, understand the application behavior, which are the network connections that have been made through all the workloads. Second step was, and it's not only about the network connections, by the way, understanding what is the process behavior, like which are the processes that are formed within this container images. And the advantage of using container images, containerized deployments or Kubernetes orchestrated deployments is that you have a atomic unit of executions, unlike virtual machines and bare metal, where you have tons of system processes executing on the same virtual machines and bare metal. You have a container image which is doing a specific task. It becomes much easier to model its behavior. Same is equally true for Kubernetes native workloads. So you get visibility into what the process forking behavior is for the application, which are the processes which needs access to sensitive assets. So you could have volume mount points. So most of the times in the containerized and orchestrated workloads, if you have sensitive assets, you need to retain it across pod restarts or image restarts or container restarts, in which case they have to be volume mounted. So these are the volume mount points which we treat as sensitive assets and then ration access to these sensitive assets. So for example, if we see that only a particular process is accessing this sensitive asset, only enable access to that particular process for that sensitive asset. So there is a learning involved in the whole process where the system learns what the application is doing, what is the behavior of that application, and then correspondingly hardens, figures out the least permissive security posture for hardening purpose. And then subsequently, we have found that in most cases, within a container image or a pod where you have multiple container images, you have tens or hundreds of binaries, but only one or two binaries or set of binaries require access to the network policies. No, not network policies, network primitives. Which are those processes which needs access to the network primitives, and identifying those and limiting access to only those processes from network communication point of view is another key impact that is done. So, so that is about application behavior, getting the recommended policies. Now, how do you get recommended policies? Like I mentioned before, we depend upon STIGs, MITRE TTPs, NIST 853, PCI DSS, and CIS. So compliance frameworks and attack frameworks put together. And then based on the learning of the app workload itself, we discover the least privileged policy. So that's how KubeArmor works. So you'll see, when we ran SEDIMENT containers, we identified what the network connections are. So you'll see ingress, egress connections, binds that are happening within all of these containers, and which are the processes that are executing within all of these containers, and what are the sensitive assets? What are the sensitive assets that are accessed by all of these containers? And again, this is a runtime behavior. We also have a set of policy templates. KubeArmor has a set of policy templates where it can go and query existing compliance frameworks for hardening policies, and that can be retrieved. Again, all of this is available in the open source itself without any. You should be able to just download the KubeArmor CLI tool and get the hardened policies in the context of the workload. Now, this is a zero trust security policy that was determined for SEDIMENT. And as you can see, there was one particular container, and I've just pushed a sample zero trust policy for one of the container, the firewall container, where there is /home SEDIMENT data that seems to be a sensitive asset that is only accessed by firewall. And this is usually what happens is that this is something which is volume mounted because it has to be retained across container restarts. So this is a volume mount point which is accessed only by a particular binary. So only that binary should be allowed access to it, and everything else should be blocked. A very straightforward way of actually modeling the behavior of a particular container. Similarly, you have process executions, right? Identifying which are the processes that needs to be executed within the container and only allowing it. So you see the action as allow here. So once you have any single policy with allow action, everything else will either get default denied or default audited based on the settings. So that's basically the aim here. How to identify a specific, how to allow specific behavior and deny or audit everything else, Well, the current status and roadmap. So the SEDIMENT demo is ready. Our intention is to show it to the 5G SBP in the next call, SBP team in the next call. The CubeArmor by itself supports all types of deployments like managed, unmanaged, and on-prem deployments. It started off with Kubernetes native environments in mind, but eventually it was extended to be integrated with edge platforms. LF Linux Foundation Open Horizon project is already, we have done a POC with them. This is when we added support for ARM platforms. In fact, today, Graviton, Ampere, as well as Raspberry Pi are actively supported by CubeArmor. We've also done integration with Intel Smart Edge. Intel Smart Edge is essentially Kubernetes native edge platform. And CubeArmor is available as a solution on that platform natively. What we are doing now, and this is where I feel we would really require some guidance and help from this community, is how do you, so we have a set of policy templates and we would ideally like to extend it for 5G needs. What we have taken is MITRE fight, and this was brought to our notice in one of the 5G SBP meeting. In fact, Mudhir sir, you brought this to our notice. Thank you very much for that. We have started plotting how some of those rules can be converted into CubeArmor policies and can be recommended for workload hardening. Similarly, we are looking at NISA 5G security controls, which were recently made available, but that is still a work in, it's not a work in progress. It's still, we have to scope out what kind of work we can do in the context. Now, one other thing is in the context of 5G workloads, like we have been working upon RAN in a box toolkit to check how do we identify customized policies for certain 5G workloads, like it could be UPF or AMF and things like that. We are first targeting XApps and then creating a set of workload policies around XApps and then taking it to other core components. So that in a nutshell is what we are. So when we started discussing with 5G SBP, our intention was to make sure that we secure SEDIMENT first. That could be the first inroads into and explaining the community as to what kind of security can be made available by these components, and then extend it for other use cases. So that's pretty much it. Any questions in the context, or any points or any feedback?
I think it's a very good roadmap. Once you build the building block with the SEDIMENT and proof, it can be done. I think the real value is going to be two-part. And the core, because it's a service-based architecture, so a lot of components have a defined interfaces that's supposed to be talking and nothing else. And similarly, you mentioned XApps, right? That's the biggest threat in ORAN architecture, is that how do you limit the behavior of XApps? Because there is expected to be very influential XApps that will change or optimize the behavior of intelligent controller in the RAN. And that's considered a new territory. And there isn't anything specific right now other than just having the communication path encrypted, monitoring the XApps behavior at the process level, and monitoring the communication, I think will harden the security of ORAN-based RAN implementation.
Right. And yet another dimension to this was, and this was brought to our notice recently, that, is it possible to shift left, when some of these components are getting developed? If this can be integrated in the CI environment itself, where the workloads, when they are changed, it should be possible for us to identify if there are new security sensitive system calls that are been introduced, or new network connections that have been added. So showing the developer that kind of view early in the life cycle would help prevent some of the some of the mishaps in the later stages. So that's another goal for this. Thank you.
Yes, indeed. So I think it would be a good tool if you can turn it after this BOC, if it can be turned into sort of in a box type of tool in a CI/CD when you're trying to do your integration testing or solution testing.
Mhm.
You can identify communication paths and the privileges required, and then go back into the architecture and review against, do we have this control built into development and configuration, or do we need something like Cube Armor to enforce it? And in some cases might be both, where you can implement the control and then have visibility through Cube Armor type of visibility solutions.
Absolutely. Yeah.
Any other questions?
Are there any telemetry you can get, Rahul, out of the monitoring aspect of Cube Armor? I mean,
Yeah. So there are three types of telemetry, or actually four types of telemetry. One is if there is a process doing socket communication, and we do not hook into network IO or system IO or file IO or disk IO related APIs or system calls. But apart from that, anything else is something that is monitored. For example, if there is a network socket communication happening, even a raw socket communication or raw socket that is open, that information is available. If there is a system calls, which are typically not used, like set GUID, set UID, or chown or chmod, these kind of system calls have been made use of, so that those are audited. That information is available. Of course, the process forking and process details are available, and the file system accesses are available. So kernel capability usage, network, process, and file system access. These are the different telemetry that is available, and you can turn on and off telemetry in the context of individual workloads. Like, you might not want to turn on telemetry in the context of Cube system names, but I'm just giving an example here. But you want to turn it on only for, let's say, UPF, say, for example. So you can set annotations in the context of that particular workload and enable telemetry. Yes, that's possible.
I was thinking more on, if let's say an API like UE attaches to the core, and the attached message is expected to be, let's say, 1500 bytes. And you learn from that all attached messages are usually 1500 bytes. When you see messages coming in, that may be of 1.5 meg or so, that will be an anomaly, right? Because that's one thing the 5G folks, whoever are, looking into and researching, hasn't really got good handle on it. What are the normal communication messages and their sizes? Because these things are, spec based. Sooner or later, everybody will realize the message with IDs and all the header parameters, they all be consistent. When it's not consistent, that means it could be a compromised message, which could either break or, have a fault issue at the receiving end and create a DDoS on that side, or maybe a remote code execution. I think that kind of capability, if you're already monitoring an interface and getting some telemetry on message size, might be a great idea.
I see. Is there some spec available anywhere, or someone or is this information available in the public domain as to that would be really great. This is something that it's very easy to extend Cube Armor to build this kind of analysis, but we require some specific points as to what kind of messages and the heuristics that you mentioned with us. So these are enormous. This is from your experience. If this information is available in the public domain, that would be it's very easy to build controls based on this.
Yeah, let's work offline. I think we're running out of time, but I'll provide you, because a lot of these specs are already given. The message formats are given in the 3GPP standards or an alliance standards. We can start building on it, because we really need to monitor for a while, like you mentioned. And then you get a standard baseline, and then you implement a rule when the baseline threshold is exceeded. Mark that as an anomaly.
Rajesh, you had your hand up. Did you have a final question you want to bring up?
Yeah, I was wondering about the time. So it's a very quick question, Rahul, and we can follow up offline.
Sure.
Do you instrument the binaries that run inside for the syscall tracing, or just run uninstrumented ones?
No. So all the binaries, essentially eBPF allows us to we do not change anything within the container images or binaries itself. So all the binaries that are executed at runtime, we do not go and enumerate the file system path within the container images, but anything that is executed, that is brought to the notice, using eBPF. So that's how we.
I see. Thank you.
Thank you very much.
Thank you so much. Real quick before we get to the closing, the SEDIMENT plus QBomber project, which was just discussed, is covered and worked on each of the 5G Super Blueprint calls, as well as all the other projects for the 5G Super Blueprint that we went over today. It's also a good platform to introduce any new functionality to any of the existing projects or something new to the community. The 5G Super Blueprint call would be the platform to do that on. As Raul mentioned, there will be a demo of the SEDIMENT plus QBomber project on the next 5G Super Blueprint call, which is Wednesday, June 14th. And we do meet every Wednesday. There's a bi-weekly call plus a deep dive call. And if anyone who does not have that information and would like to join, reach out to myself or any of the LF staff that you know, and we will get you connected with the tools and the resources and the meeting invites. And with that, Kenny, Heather, I'll hand it off to you.
Yeah, so I would just like to remind everyone to register if you have not registered, to fill out the event survey if you have not filled out. Well, sorry, I'm sure very few of you have because we just kicked off the event, but to fill in the event survey, to everyone for the sessions that you hosted, to please place a summary on the daily summaries page. Reminder to upload your recordings and slides to the appropriate area on the wiki, and to attend our town hall, where we're going to be talking about sort of one of the general themes that's running through many of today's presentations, which is the collaborative nature for a number of these solutions across multiple projects, both within LFN and outside LFN. So those are sort of, need to probably whittle that down to 3 so people can remember it, but the sort of the main things that I want everyone to carry away from, as well as to once again reiterate my thank you to all the presenters today, and thank you to our programming committee. Kenny, anything else on your end?
Thank you, Heather. The only thing that I wanted to highlight is tomorrow's session at the end of the day, which is an Ask Me Anything panel for the LFX platform. I will drop the link into the chat window. So if you have questions that you'd like to ask and you want to do it beforehand, just drop your questions into there. That'll probably help get things rolling when the session starts. That's it. Want to thank everybody for your attendance and your participation. Great discussions today.
Thank you.
Thank you, folks.
Thanks, everybody.
Thanks, everyone.
Thanks, everyone.
Thanks.